presentation
Okay.
and shorter with the second.
Okay. Welcome back. If you could all take your seats, please. We will go to the home stretch. Okay. We'll gather the stragglers from the lobby. For those of you on the web, again, comments can be sent to auditorium@calipa.ca.gov. And at the end of the day, we'll post the website. So I've been assured that there's been a lot of questions about where you can find the audio and video presentation for the last 2 days. And we will post those on that drink website as well. So at the end of this workshop, you'll be able to see everything. The presentations will be there as well. And I'll post the address web link again. So let's see. Now we have Chad. Okay. So this is the ion exchange treatment background. Chad Siddell, Manager of Water Technology, Jacobs Engineering. Take it away.
Thanks, folks. Hopefully you're not getting sick of me and all my op-ed commentaries. Eugene asked that I give this presentation to provide some context for the ion exchange technology discussions that will follow. And so that's my intent here, is to provide that high-level overview. There's a fair bit of good material here, again, that comes from the materials that we developed with the AWWA and SBX1 related efforts. I really want to credit Dennis Clifford, in my opinion, one of the primary godfathers of ion exchange research. If you do a lit review for ion exchange treatment, particularly for inorganic contaminants in drinking water, his name is all over that, as well as a couple other key folks. And so Dennis is a great guy, and these slides are really more his than mine. I'll point you again to these good resources that point out a lot of this type of information, and good references to have at your side. And so back to the family tree of nitrate removal and treatment options, the family tree, so to speak. This is focusing on that small portion of the tree for nitrate removal for ion exchange. So we've got those options of conventional ion exchange using standard strong base anion exchange resins, specialized resins that are more selective for nitrate, using improvements in the regeneration approach, such as countercurrent regeneration, advances that use multiple vessels operated in parallel and sequence regeneration to improve upon the efficiency of the process and minimize brine waste volumes. And then last, weak base anion exchange as well and its potential application. So I'm going to give very high-level overviews here. So ion exchange, as we described very briefly yesterday, is a resin-based treatment technology. So these are very small, 1-ish millimeter sized resin beads, polystyrene type beads, that have functional groups that will remove anions. The most commonly used approach is strong base anion exchange resins, or SBA, operate in a range of pH conditions, but most notably in ambient water quality conditions for typical groundwaters. It's important to qualify the fact that weak base anion exchange, which can be used for nitrate removal, although is not used for that application in full-scale applications today, has to operate at a much lower pH condition, and that is why it's not really used. These resins are typically applied in fixed bed columns, so pressure vessels, downflow, exhaustion and regeneration, where you've got the water flow for treatment and then the brine flow for regeneration. If those both go downflow, we call that co-flow regeneration or co-regeneration, or that's a conventional approach. You can do counter-flow exhaustion regeneration, where you have, again, treated water going top to bottom in a downflow mode, and then the regenerant itself is going from bottom to top. The theory behind that is if you are loading the contaminants from the top down, they're most concentrated at the top, so rather than trying to push them all the way through the bed, through the resin bed itself, you just push them back out the shortest path possible. Mixed or multiple fixed bed columns in parallel can improve some of the efficiencies, and we'll talk about that. And then there's the continuously mixed flow reactor, which will be talked about a bit more by the folks from Orca here in just a bit. When we come to talking about brine management, these resins are, for a strong base anion exchange resin, which is the focus of this remainder of this session, typically they're regenerated with a sodium chloride solution on the order of perhaps 6% at the lowest concentration, and sometimes they're regenerated with much stronger sodium chloride concentrations. There are some advantages to lower and higher concentrations and the approaches taken towards regeneration that can limit the overall brine waste, such as partial regeneration or the reuse of the brine after it's been used to continue to use it and decrease the total disposal volume. And then there are approaches that denitrify that brine and in some cases render it reusable for primary regeneration again later. And there's going to be some talks that will highlight that, I know, that will follow. So strong base anion exchange uses anion resins operated in a chloride form typically. I'm not going to talk about bicarbonate form resins here. But, you know, when you start out, you've got nitrate that replaces one of those functional groups that's holding onto a chloride. The nitrate sticks to that functional group, and then the chloride is released into the treated water. Regeneration just pushes it back the other direction, where you just have a really, really high concentration of chloride that from a concentration gradient displaces those nitrate anions because of the concentration pressure. And then you displace that nitrate and put a chloride back onto the functional group. You know, it's fairly simple. It operates fairly well in terms of on-demand operation. These are not systems that have to be operated continuously, although, you know, just from operational experience, they're simpler to keep operational and maintained when they're operated continuously. But these are systems that you can turn off and turn on. So for small wellhead systems that have that requirement and you don't have a storage tank, like what we talked about yesterday for biological treatment systems, these systems can meet some of those expectations. There are some issues that need to be resolved, though, with strong base anion exchange treatment for nitrate. One is nitrate peaking or dumping that occurs. If you operate standard strong base anion exchange resins that are not selective specifically for nitrate, if you allow them to be operated past the point of breakthrough, which means the raw water concentration meets, or the treated water concentration is then equal to the raw water concentration, if you operate past that point, other anions that are more selected, namely sulfate, can displace the nitrate that's been removed and push that off into the treated water. That's not so much of a concern for nitrate treatment when you're doing so for primary nitrate treatment purposes, but for other contaminants, for example, arsenic or hexavalent chromium. If you apply a strong base anion exchange resin that operates past the nitrate breakthrough curve, you will peak nitrate off of that standard non-nitrate selective resin. Now, of course, you can use nitrate selective resins, and I'll get to that in just a second. Regeneration can be inefficient, and it can use a lot of sodium chloride. Much of the conversation this afternoon is going to focus on making those things be more optimized and resolve those downfalls of the treatment process, and ultimately what happens with the disposal of those things. So here's some pictures of some typical strong base anion exchange resins. Again, polystyrene, divinyl, benzene polymers. They have amine functional groups. Typically, they're in the 0.5 millimeter to 1 millimeter size range, maybe 16 to 50 mesh. On the left, you've got macroporous resins that are opaque, and on the right, more gel-based resins. And I don't have the picture in here that shows a whole range of commonly applied commercially available resins today, but they span the gamut of these. You typically can go to any resin supplier, and they will have their quiver, so to speak, of strong-based anion exchange resins that are optimized for removal of various contaminants, nitrate certainly being one of those. So here's a simplified process flow diagram. You've got water that comes in the top of the contactor here. The resin's initially in a chloride form, and as you step forward here, you take your nitrate contaminated feed water and the initial flow goes in. Sometimes you design these systems with a bypass that's not treated, so perhaps you're only treating 75% of the flow. If your raw water nitrate concentration is just at or just over the nitrate MCL and you want to target commonly what DPH would prescribe about 80 to 90% of the MCL on the treated water side, you could treat the treated process flow to a very low concentration and allow the untreated water to blend and bypass. So that's an important step shown here with that bypass water. So you've got your nitrate-free ion exchange treated water on the back end of that, and then the blended water, typically here, you know, in a nitrate as N value of 5 to 7 milligrams per liter, or say 25 to 36 milligrams per liter as NO3. Now when you go to regenerate, you're typically using a sodium chloride solution that's on the order of 1 to 2 molar, 6 to 12%, and then that goes either upflow or downflow. In this case, pictorially shown as downflow, so co-current regeneration, and it will push off the resin or the nitrate into the brine, and then you've got your spent regenerant. Now, all these other things, sulfate, nitrate, chloride, bicarbonate, and lots of other inorganic anions, arsenic, uranium, perchlorate, chromium, selenium, and others there, including total organic carbon, will get removed as well, and it's important to keep that in mind. So when we think about the scientific application of strong base anion exchange, you don't usually think about it in milligrams per liter, you think about it in milliequivalents per liter. So that is the negative charge of the anion you're considering. So, and for all the background ions like sulfate, they compete with nitrate based upon not just their concentration, but by their equivalence. You know, sulfate has has a -2 charge, and so it can outcompete not only because of selectivity, just because of charge in some cases. So the more you have of other competing anions in the raw water, typically the less effective ion exchange is for the treatment of nitrate. There's things that can be done to overcome some of that, but that's where, as you have higher and higher concentrations of competing anions, sometimes other technologies that we've talked about here can become more cost competitive, but typically strong base anion exchange starts as one of the more cost-effective approaches. For example, to demonstrate this is work that Dennis Clifford and others published probably 25 years ago that shows the impact of sulfate concentration on the nitrate run length in bed volumes. Typically, you know, if you have, say, a 50 milligram per liter sulfate concentration, you might be achieving somewhere on the order of 400 to 500 bed volumes. Now, there are waters that are cleaner that achieve more than that, 700, 800, even 1,000 to 1,500 bed volumes for nitrate removal if it's a relatively sulfate-free water. But as you increase those other co-occurring competing anions like sulfate, you decrease the run length. Now, this gives you an example of that selectivity sequence. Sulfate preferred more so than nitrate over chloride and over bicarbonate. Those less preferred ions will quote-unquote peak. And because nitrate is less preferred than sulfate in a standard strong base anion exchange resin, it does have that potential to peak higher in the treated water than in the raw water if allowed to operate past that point on the breakthrough curve. And I believe here's a picture of that. Here we have two breakthrough curves for a single resin operated in a case where there's nitrate at approximately 15 milligrams per liter. Nitrate is N. And as you'll note, initially you start seeing breakthrough at about 200 bed volumes because, as you'll note, this is a pretty high sulfate water, 150 to 200 milligrams per liter sulfate. And because that sulfate outcompetes for that nitrate, once the nitrate's been removed to its exhaustion point, the sulfate starts displacing the nitrate, and that's why for a short period of time, you have nitrate concentrations on the treated water side of an individual vessel that will be higher, approximately 2.5 times higher than that of the raw water. Now, these are all things that can be designed around. There's really 3 ways to eliminate nitrate peaking. One is use a nitrate selective resin. And these are resins that have different functionalized groups that influence the selectivity sequence that makes sulfate more preferred or nitrate more preferred than sulfate. It makes the process a bit more difficult to regenerate because the resin does a better job of holding onto the nitrate. It doesn't want to release it as much, and so there's some impacts there. You can also operate multiple columns in parallel at different stages of exhaustion, and this is simply a means to blend down that nitrate peak. And if you have nitrate in the treated water that peaks to, say, 2.5 times the raw water concentration, you just need to have enough vessels to blend it down to keep your blended concentrations close to your treatment target. And the last thing is you can use a completely mixed flow reactor, and there are benefits with those to avoid peaking not only of nitrate, but any other contaminants that might peak in the process stream. So nitrate selective resins, they change the sulfate affinity, decreasing it by increasing the charge separation between those sites. This is probably way too technical, but there are lots of really good scientists, in fact some people that represent those groups in this audience that can speak to this more specifically. But it simply just makes nitrate more selected and allows it to operate more efficiently in the presence of sulfate. So here's that breakthrough curve for a nitrate selected resin. So sulfate breaks through and peaks as well, as noted by this slight increase of sulfate for that period. And then nitrate doesn't peak. It simply reaches the initial raw water concentration and is stable at that. There are advantages to doing so, and you then would operate, if I go back here, this initial water, we were operating a breakthrough curve at 10 milligrams per liter nitrate as N or 45 as nitrate at about, call this 280 bed volumes of treatment operation. Here, we're operating that more so at, say, 320. So you get a little bit longer treatment, and you then have the opportunity to avoid the peaking. Now, multiple parallel columns operating can eliminate peaking because they're just at different stages of exhaustion. So these are systems that are on a carousel or valved in a way that allow them to be sequenced. And it just simply smooths out that peak in the treated water that's all blended together. Upflow regeneration and partial brine regeneration and rinse can also conserve the salt and reduce that disposal too. So let me talk about that. Actually, here's the description of operating columns in parallel. You know, you might have somewhere between, not necessarily 2, more like 6 and 20, 5 or 20. And as they are operated and they achieve breakthrough, one of them goes into regeneration and the next one that was on standby goes into operation. And so when that one goes back into operation, its neighbor is already past the nitrate peak and it has the ability to blend down those concentrations. Now, this is this is an old version of a continuously mixed ion exchange flow reactor. I'll leave it to the folks from Orica to give their current version of this, but simply stated, rather than a packed bed column-based application that allows for peaking to happen, all of the resin is simply suspended in a completely mixed reactor, either in an open atmosphere as described by this example, or more commonly for groundwater inorganics, they're now operated in an upflow pressurized vessel mode. The difference here is that the resin is not regenerated in the primary treatment path. So here water comes in on the left, goes through the CSTR, resin's recovered, and treated water goes out the back end. The resin is removed physically from this process and regenerated outside of the primary treatment process. So all that salt that you push through a primary treatment pressure vessel for a standard packed bed column is not put directly into the process flow. It's done so outside in a resin regeneration tank. And that gives some flexibility for the regeneration process that packed bed systems don't have. So I think you'll hear a little bit more about that. Has advantages, and it's just a different way of going about it. Now, regeneration of the spent resin. Sulfate's pretty easy to push off of these resins due to a phenomenon called selectivity reversal. Other things that are divalent anions, like chromium-6, are also easy to push off of strong base anion resins because of selectivity reversal. But other monovalent ions like nitrate don't undergo that selectivity reversal, and so they can be harder to displace off the resin with a strong sodium chloride solution. And the higher that selectivity ratio of nitrate to chloride, the harder it is to regenerate those resins. So for the advantage you get for using a nitrate selective resin, you get the disadvantage of needing more salt to regenerate it. You know, more pounds of salt per nitrate removed in cubic foot of resin you've got to begin with. Here's an example of how you elute off the sulfate and nitrate. The peak for sulfate is much sharper because of that selectivity reversal. Nitrate takes longer because it doesn't have that phenomenon. And this is just a representation of regenerating a system with, say, a 6% sodium chloride solution. And that says what I just said. Now, last couple of slides here are there ways to make this process work better? And sometimes, particularly for small systems, they take the approach of if some salt is good, more salt is better. That's not always the case. And it is important to evaluate systems in terms of their treatment efficiency on the basis of how much water in total and how much salt in total is being used to operate the system efficiently. Sometimes backing off in both of those ways ends up operating the system more efficiently to achieve your treatment target. So here's an example. At 6% sodium chloride, you get sulfate off, versus at 12%, you get sulfate and nitrate off it that way. And because these lines are not on the one-to-one line there, that's kind of why you see sometimes you get less efficient operation of those systems that way. Now, there are solutions to this. In some cases, some of the folks that are going to speak today utilize these approaches to improve the system performance. Partial regeneration, where you use less salt and less volume to not remove all of the nitrate on the resin, can be more effective. That usually results in a higher treated water concentration after regeneration for nitrate, but if it's still lower than your treatment objective and it operates for longer, that can be better in the long run. That does have the possibility of precluding blending, so you got to think about this from a macro level view of the problem to understand what's the most efficient way. Upflow regeneration, as I said before, can help minimize the brine, and we already talked about parallel and countercurrent. Now, another area that's seen a lot of research in the last decade or two, gosh, longer than I've been involved in this, so a long time, includes denitrification of the brine and then reusing that. Heard a lot yesterday about biological denitrification of the primary treatment flow. This is thinking about using denitrification approaches, either biological or chemical, to remove the nitrate from that spent regenerant and then reusing that spent regenerant over and over and over again. And that can work tremendously well if you can keep some of the other competing anions out of the equation, sulfate being the worst actor. And some have demonstrated better experience with that than others. And I think, in my opinion, this is the area where getting research from universities and from technology developers into the field has the opportunity to truly change the way that strong base anion exchange can be applied, not just for big systems that have lots of operators, but for small systems that just can't manage the logistics of getting salt deliveries and brine disposal tanker truck schedules managed. Has the potential to reduce the brine volume and decrease the overall salt consumption. So that's what's going on there. So in summary, strong base anion exchange is certainly a technology that can be used well for nitrate. If you're implementing strong base anion exchange for nitrate removal, because nitrate is not as selected as the other contaminants listed here, uranium was mentioned earlier, chrome-6 has been mentioned, arsenic has been mentioned. If you operate a strong base anion exchange resin to remove nitrate, you are going to get removal of all of those other co-occurring contaminants if they're present in the water. So, for example, as the reverse osmosis point of view systems have the advantage of decreasing the TDS, which is a good aesthetic benefit, this approach has the public health benefit of reducing exposure to those other contaminants if they happen to be present and of concern. And we'll hear a lot more from the upcoming speakers about ways that technology developers are advancing kind of the application and the state of science of these approaches as described here. And I really do believe that while, as I showed yesterday, the vast majority of nitrate treatment systems installed in California, frankly in the US for potable water treatment or ion exchange, there's lots of room for improvement of that technology. And while current treatment costs for standard strong base anion exchange applications might be on par with some of the other technologies in some cases, whether it be reverse osmosis or biological denitrification. The opportunity to decrease the capital and O&M costs for strong base anion exchange is still very tremendous. There's lots of opportunity for improvement, and hopefully, this is just a challenge to those in the audience working on that. Keep up that work, because as we drive the cost down of that technology, the more affordable it becomes. So, hopefully I didn't steal the thunder of everybody else. Let the others take away on this message, and I'll listen to what you all have to say. Thank you.
Thank you, Chad. So next we have small water system economics for near zero liquid waste denitrification, Phil Chandler and Mike Waite with INX SG Limited.
Thank you, Chad, and good afternoon, everyone. My name's Phil Chandler from INX SG. My learned colleague here, Michael Waite, is the man who's our technologist, so I will be deferring questions to him at the end if they get too tricky. He is my phone a friend for the presentation today. What I'm going to take you through today is the net result of 10 years research in Mike's case, but in the last 2.5 years work that we've actually done in California, principally from a pilot study that we did up in North Davis Meadows with UC Davis back end of 2010, 2011. The takeaway that I've had through the working on this pilot, and also traveling through and talking to quite a few people sat in this room actually about the issues of small community, really echoing Chad's points, is about looking at the brine management and the salt delivery to the site, and to making sure that you can look at the economics of physically running what is a relatively complex system in terms of a service engineer training requirement. We believe that we've produced a product rather than a project in a 20-foot container footprint that will arrive in Davis in 3 weeks' time. It's currently on a boat on the Atlantic. And we have two methods of reducing the operational cost of ion exchange. Our first one is that we look to optimize, especially the removal of the competing anions that Chad eloquently put just now, is to look at selective regeneration, which we've done on full scale on public water, drinking water treatment systems in the UK, and that we can reduce the operating costs by stopping the sulfates and the bicarb fraction of the eluted regenerant from going into the truck that goes to the waste. By doing that, we think we can bring just the operational costs down to $270 per acre foot, that I'll describe in some detail, how I arrive at that number later. And then, uniquely, we also have a near zero waste brine recycle system, which is an electrocatalytic cell, that we initially trialled up at North Davis Meadows. We completed 15 reduction cycles using this and reusing the brine. And we feel that with that, with the near zero waste, that we can get to a target of $149 per acre foot. The system that is arriving is actually a product that's ready to go. It's a fully PLC controlled with continuous drinking water monitoring through nitrate analyzers, and it's something that we're going to drop on top of the well, and we're going to have it started up in a few days, and we're going to use that to go through conditional acceptance with the CDPH folks to actually prove both our performance claims and, of course, that we're producing quality water. The electrochemical cell I'll be talking about is NSF approved already. We've spent the money on doing that, and we're looking for the program to start in 2013 for our conditional acceptance. I guess I'm going to sum up Chad's presentation of 23 slides in one cartoon, which I do apologize. So the two key methods for us are that we're looking for a sulfate return that we selectively remove the competing anions off the resin bead. The picture on your right shows that little resin bead expanded and showing you the labyrinth of sites that you can collect the nitrate, the sulfate, and the bicarb. The sulfate and the bicarb, my colleague here from his work in the British nuclear industry, proved that they're more labile on the resin bead. They're easier to remove with a very, very dilute chloride solution. Our methodology for regenerating the ion exchange columns in a multiple column system, I'm trying to see where my red dot goes. So in our system, it's a 3-column system. They go round in a merry-go-round, so you've got a lead lag. You've always got that backup of the columns capturing any leakage from a column going to exhaustion. We selectively remove the more labile the sulfate and the bicarb into a tank that in the UK, we drip back into the product water output. So instead of that going into a tanker and being disposed of, that is now returned to where it came. We have 2 full-scale systems working in the UK since 2006. A third is due to come online in 2014. And that key improvement reduces the amount of waste as a percentage of the product water throughput down to about 0.12% of throughput. A good ion exchange system without this feature is running at about 0.5%. I'll come back to the impact of that on the economics of running a small system in a later slide. Uniquely to us, then as was said earlier, to actually displace the more difficult to shift nitrate from the kernel or the resin bead, you have to hit it with a much more concentrate chloride solution to break the bond. So that waste, which is the concentrate salt plus the nitrate, is something that we will take to an internal tank on our system, and that will work through an electrocatalytic cell, and we reduce the nitrate NO3 in that solution to nitrogen and oxygen gas. That permits the reuse of the brine for further regenerations and eliminates that one-shot use of the brine going to the truck and the disposal site. So this is what the system actually looks like that's coming over. So we have the 3 ion exchange columns, each with 7 cubic feet of resin. We have an onboard water softener for water makeup, so we don't actually introduce any hardness into the ion exchange. And also on this system, we have the tankage and the valving to actually permit the selective regeneration of the system to elute the sulfate and drip that back under controlled conditions into the drinking water output. Squared away in the little corner there is the electrochemical cell. The concentrate brine, the second stage of the regeneration of the ion exchange. The brine is actually passed through that cell. I'll talk about that in a little bit more detail in a few slides. But within this 20-foot shipping container, so just think about the little shipping containers, not the big 40-foot, the little 20-foots you see rumbling around. It's a CSC rated, you can ship it anywhere on the back of any truck, ready, fast to deploy system. So within the small community system, as we've approached this design, is that we've included the 3-column ion exchange, 2 nitrate analyzers. One's continuously on the treated water output that people drink, and the second one is monitoring for the system operation inside, looking for the breakthrough and the leakage of nitrate out of the columns. The electrochemical cell is NSF certified, and we also, on this one, because of the well we're going on, have an extra column to incorporate and remove hexavalent chromium to less than 10 ppb. Sulfate, we've been doing that since 2006. The top picture shows an 800-gallon-a-minute system near Cambridge for Affinity Water, who are our public reference for this. It's UK government approved. And the sulfate return and the reduction benefits that gives are one of our key first conditional acceptance tests and validation that we're going to do in Davis in the next 3 months. The return on doing this is that we can reduce that waste volume from 0.5% to less than 0.2 to maybe 0.12%. It's a well-proven technique in the UK, and what we've done is simply Honey, I Shrunk the Kids. It's now squeezed into a 20-foot container, which is capable of a 50-gallon-a-minute output. So the numbers of where I got the $270 an acre foot and the 83 cents for a 1,000 gallons of drinking water, there's a kind of a bit of data on here because I'm the sort of person who likes to go and follow trucks to East Bay Mud and find out how much people pay for stuff. So given the example that the CDPH folks gave us of looking at 50 gallon a minute with a 60 milligram per litre as NO3 to 36, If we look at just a 3-column ion exchange system with just the sulfate return, then of course we're going to use sodium chloride for regenerations. We're going to need power to run the internal pumps. But the real kicker, if you're at the back end of Visalia, is that even at 0.12% of brine, you're still looking at 7 to 10 tankers trucking that waste away from you to go somewhere. And the fundamental problem with brine disposal, if you imagine a 0.5%, it's going to be much higher than this, is this little calculation down the bottom from Advanced Chemical Transport, fairly typical for me. So for that person to turn up with their 5,000 gallon tanker and collect your waste, it's $105 an hour. It's an 8% fuel surcharge. And then you've got to get it from an awful long way down into the Central Valley out to a disposal site. And so that is the great variable and the great cost in operation cost of looking after an ion exchange in a rural community. We are releasing this product in this form after conditional acceptance, because there will be sites where the economics work out pretty well for just this capital investment. But you will need to provide a brine tank, which I'll add into the calculation of costs in a few minutes. And you do have to consider looking after, essentially, a frequent collection of waste and the operations management of the administration looking after it. So if the brine is a real issue, then the unique part of what we're doing is that we can reuse the brine through electrocatalytic reduction of the nitrate, the NO3, in solution to nitrogen oxygen gas. I'm not going to spend more than 1 or 2 minutes just going through what this cell does. It's something that Mike has spent 10 years of his life working on. My job has been to dumb it down and get rid of all the science bit and make it a robust piece of kit under a control algorithm that can survive a whole bunch of different operating conditions of temperatures, pressures, and flows. In essence, it's a bipolar cell. We have 2 end electrodes. The electrodes are coated in rhodium, nicely inexpensive precious group metal, which is a very effective catalyst for the reduction of splitting apart the NO3 compound into nitrogen and oxygen gas. And by doing that, we're actually taking that concentrate brine and just creating effectively oxygen-rich air as a byproduct. Once we've reduced the nitrate concentration, then that is good to go, and we will then reuse it for further regenerations on site, all within the 20-foot container. The impact of doing the brine reuse is quite marked, is the fact that now, instead of having 34,000 gallons of waste, you're down to 2,000 gallons per year. And our biggest benefit of doing this, we feel, is that as a company, we understand and have looked in quite detail at the problems in rural communities of looking about the operation of the system. It is a complex system with an electrochemical cell and all the additional valves. So what we're looking to do is to provide specialist services that periodically the brine will reach a point that other materials in it have got to saturation point that we need to replace that brine. That's something we feel that to avoid a T3 classification is that we, as our company, will provide that as a service, and the costs up there are for to do that on site as a specialist service. The costs for the nitrate analyzer calibration come from Huck. We actually do this work ourselves on our own pilot right now. But the net impact is that you can eliminate the brine. You also reduce the salt drastically as well to the sort of tonnage that you can put on the back of a pickup truck. And if you start to think about the economics of a small well being tucked away in the back of somebody's land, then you're starting to kill off all the infrastructure issues about trying to get a 5,000 gallon tanker reversing up a street and parking next to a well and the collection of that waste. So the combination of the sulfate return and the electrochemical cell is something we feel is quite unique and is very much a huge, I feel, benefit to that type of installation where the infrastructure and having a ready, rapidly deployable piece of kit is going to be something to eliminate the nitrate issue. So the way that we have been executing these projects on a smaller scale and wish to execute them in future is that the roadmap for us of addressing and first contact with an impacted user is to look through that state resources revolving fund listing to actually speak to the folks down in the Central Valley and start. Obviously, the first port of call is that we do have data available on paper about what the water well actually has in it. But I think we have right now down in Santa Cruz are what we call a Pathfinder pilot system, a 20-foot containerized system, which is rather cute because inside it's got glass ion exchange columns, it's got an electrochemical cell, it's our science unit. And what we're offering within the pricing that I'll be talking about in a second is that we see that once we understand on paper what's under our feet in the groundwater, we would park this 20-foot container on the well and actually run it ourselves for 3 to 4 weeks, as we have done 6 times now, and look at what's in the water. And we can also use that with the glass columns to bring people in, get them comfortable with what ion exchange is and what the water flows go through and all that sort of good stuff. And also our chemical engineer happens to be Spanish, which I'm kind of curious actually, is if when I get down there, the language barrier is such. My original idea of employing a Spanish engineer was to actually train the service folks in these communities on the more complex aspects. But I'm starting to think actually with the whole community show and tell side of this, that's going to be kind of interesting to see if that provides a more immediate understanding of the folks there about what we're trying to do to clean up the groundwater. The preparation is, in our world, is that we are putting a system on the street corner in Davis. We need to find service providers to deliver the chemicals into the system, and we need to provide the service to actually remove that brine. And we have chemical suppliers prepared to come up to our bulkhead connection on the 20-foot container and treat it like filling the gas tank, with that milk round idea that you come round and you load up, for example, if we need HCl on board our system, because that's how we do a pH adjust after we regenerate the brine, is that we're looking for a hookup of some supplier, and we have 2 interested in doing this, where they do it themselves under controlled conditions and they can see the condition of the onboard tank to refill. Delivery and installation, that's something that I personally do at the moment, which is quite fun with Lawson Drayage over in Sacramento. We can, within 2 hours, we can have the unit off the back of the truck and located on the ground. And then we're also looking to include, to support the training of the operators and also to look at the transfer of the conditional acceptance into real data testing to get a permit for that particular installation or within our scope of supply. I won't dwell on this too much apart from one little story, is that when we talk about co-contaminants, and yes, there's a laundry list when I look down the list, and it all becomes too much to bear, and it's going to be this big train of treatment technologies. We faced at North Davis Meadows hexavalent chromium in the groundwater, and we didn't actually expect that, and it was an interference on the way our electrochemical cell worked. We overcame that, and at the moment, working with the Water Research Foundation, we've leased our equipment to, and the work that we're now doing in Davis, is that we've turned that problem into our solution for removing hexavalent chromium from groundwater in combination with nitrates. And that's something we certainly will be doing in the Davis pilot, is looking to find out the operating costs and publish those for that. There was talk about blending earlier on. In the UK, when we've been talking to folks about water treatment, the transitory nature of the communities that you're in, you've got seasonal swings in nitrate, you've got large population shifts, you've got large amounts of demand on the water in some seasons and not others. In the UK, there's quite differences in the amount of draw and the impact of nitrate concentration. What we're finding with the automatic blend control and the fact that we monitor and control the flow into each column is that although we're looking at a 60 to